All right. Hey everyone, my name is Bobby Filar. I'm a data scientist at Elastic working on the security product there. I'm joined by Ed Raff and his myriad of organizations he represents, and we're here to talk to you today about using passive-aggressive methods to combat false positives in local environments. Now, before we kick off, I kind of wanted to provide a real-world scenario or an anecdote kind of from my professional life building a macro malware classifier. And it's really the impetus behind why we kicked off this research to begin with. For those of you who don't know, macros are pretty pervasive across enterprises for task automation within Microsoft Office documents. They allow you to build forms or buttons and calculations and things like that. And they're used quite a bit. But they're also used quite a bit by malware authors to arbitrarily execute malicious code. And it's become a pretty powerful attack vector for things like phishing attacks. Now, the security industry would normally or historically use like hash-based approaches for detection prevention or reduction of FPs. But it's really, really hard in this environment because these hash-based approaches don't generalize, because the minute you edit a document again, you change that hash, and that creates quite a problem when trying to detect things more broadly, which is where machine learning represents probably the best opportunity to generalize and start to detect these unknown threats at scale. So what we did is we applied, your kind of traditional supervised learning approach to getting this model into our security product, where we collected a bunch of data from a variety of sources to get a representative sample. We employed domain experts in the form of reverse engineers, or threat researchers to help build out features for feature extraction. We trained a model. We internally validated it, which is where you get the marketing 99.9% effective. And then we pushed it out to production. Now, the question becomes, when those start getting used by users and you come across FP bursts and things like that, how do you improve your model after the first time it's gone out? You can collect more data. That's certainly an option. You can take time and money to extract new novel features that attempt to identify new families or subclasses of the problem you're tackling. You can retrain a model more often, or you can wait for a bunch of FPs to roll in and do a big update then. Now, all of these take a fair amount of time, energy, and dollars to accomplish. And at its core, it highlights the biggest problem with a lot of security products these days. It's that false positives are the biggest concern. It's the biggest concern for me. It's certainly the biggest concern for users who have to deal with kind of alert deluge and these bursts of FPs. And we, as an industry, have a couple of big challenges to deal with, particularly with ML. And it's, once these models get pushed out to production, how quickly do they start to go bad or decay? And once you understand when they go bad, can you figure out why? What causes models to start to spoil or cause these big bursts of false positives? Is it like a software update or something like that? Firefox or Chrome or a piece of enterprise software? Is it an operating system update like a Patch Tuesday? And once you understand that and start to see that, you see a larger issue kind of at hand. And it's this idea of data scientists and machine learning researchers building these global models trained on a representative distribution of data of what we expect local environments to look like, versus the reality, which is local environments are extremely noisy, and there's custom in-house software and proprietary data everywhere that we will never see anything close to that kind of in our training data set. And it does things that look inherently malicious. So we as an industry really have two options at our disposal right now. And option one is putting the power back in the user's hands in the form of allowing them to allow list or deny list something. And this works. They can use like a file hash or a certificate signer to basically play whack-a-mole. It's this sort of one-to-one relationship where a hash equals a file or sample. But this doesn't really generalize well, and can be very time consuming and very frustrating from a workflow standpoint. Now, option two, which is called just like give us all your data, is certainly the better of the two options, because this could yield massive improvements over time in a relatively short amount of time. But it comes with some pretty big concerns in the form of privacy. We as data scientists need to be very careful about the data that we use or leverage for things like GDPR or other proprietary data. We also have to look out for end users to make sure that we're not hindering performance, taking too much bandwidth, shipping data back and forth across the wire, degrading performance on the endpoint by packaging up these files or samples in order to send them back. These are things that we really need to be mindful of. And that's really what Ed and I were talking about a few months ago when we came up with this idea. We wanted to explore alternatives to kind of the more traditional FP triage approaches. And we started hovering around this idea of leveraging the security worker as the domain expert, but the domain being their local enterprise, their ability to know what belongs there and what doesn't belong there. And take that knowledge and turn it into kind of an iterative human in the loop active learning exercise where we give them the tools that data scientists bring to the table in the form of feature extraction and model training, and allow them to just capture the files that they're interested in not alerting on anymore and updating the model locally. And I'm hopeful that this kind of tailoring or customization would lead to a better overall security experience for the end user while maintaining the privacy of enterprise data. That data never has to leave their environment. So how did we do that? I'm going to have Ed take over now, and he's going to walk us through it.
So in order to fix these problems, to fix these errors, we think we're going to need a linear model. And part of this is because for tree-based models, which is what the current method uses, there's not a lot of good ways to update a tree-based model. There are approaches to it, but they require multiple errors in order to cause the model to really change its decision surface. And we need to be able to correct an error and immediately know afterwards that it is no longer an error. And that's much easier to do with a linear model, where we can just know that the hyperplane is now adapted. And we also want to fix the likelihood of future false positives, or make those less likely. And that's also easier with a linear model. We could force a decision tree to carve off a little tiny hole in the world for just the false positive, but that reduces back to basically a blacklist, which is not what we want to be doing. One approach might be to take the false positives and create sort of a radius around them, where you decide this is what this area now becomes a benign area rather than malicious. But then it becomes confusing on how do we pick this radius, because we don't want to rely on the local information, because that local information, according to the model, was already somewhat wrong by the nature of having a false positive. And this could also map to one-shot learning, which we'll test as an alternative approach, but we find it doesn't work as well. So what we ended up using is what's called the passive-aggressive algorithm, which comes from online learning, and the goal is that we want to make a change in the hyperplane to correct a current error. And the naive passive-aggressive algorithm attempts to fully correct this error while making the minimum possible change to the norm of the weight vector. And this is sort of a good mental trade-off. Like we want to fix it, but fix it by changing as little as possible. Now, normally, you wouldn't ever actually do this. And the original passive-aggressive paper introduces a regularization penalty C to prevent it from fully correcting on errors. Because if you get one mislabeled data point and you fully correct it, you could end up destroying the model. But in this case, we need to fully correct after one update. So we're going to do something weird and use the unregularized version of the model. Now let's go through a toy example to show why. So you have some false positives, a few come in, and you want to correct them. So if you do the naive approach of just stochastic gradient descent, you end up with some moved hyperplane, which induces many new false negatives, which is not as good. So what we're going to do instead is the passive-aggressive update, where the new vector, or the new weight vector, is the minimum norm change, and then this gets us a better overall solution that corrects the errors with hopefully minimal new false negatives. And now we have a model that's been adapted to the local user. So that's basically the strategy. And our initial solution, some inspiration for it, we use malconv. So malconv will convert the macro code into a fixed dimensional feature space, where we can then use the linear passive-aggressive approach on top of that. When an error occurs, we update the passive-aggressive model on top, not malconv. But then we have this question of how do we prevent users from creating false positive updates. So they say it's a false positive, but they were wrong. And that could potentially destroy the model. And the hope is that all of the difficult things are on the border, and so wouldn't need large changes to the model to fix them, but we still need to address this scenario. And what you see here, the black X's mark 58 particularly difficult false positive files from production real live data. So in order to solve this second problem, what we do is we use k-means to estimate the impact to a model's accuracy if the model's been altered. So we can use the weighted centroids and their label purity to estimate the AUC. And this is actually a pretty good estimate. And it's not hard to compute, and that way we can share these cluster centroids rather than sharing the original data, which also helps maintain privacy and avoid sharing proprietary data. For evaluation, we'll have 650,000 benign files and almost 450,000 malicious samples, and a special held out hard false positive set of 58 files that I mentioned previously. The baseline results is that the gradient boosted decision tree is the most accurate on the data, which is not that surprising. It's on the engineered features produced by domain experts. Malconv with passive-aggressive or stochastic gradient descent on top doesn't do quite as well, but does decently. In particular, it's got okay true positive rates at a fixed 0.1% false positive rate. The malconv plus prototype is testing a one-shot algorithm approach to dealing with the false positives. And you can see it actually learns degenerate solutions and has really poor performance. So that makes it a no-go. We also attempted the passive-aggressive algorithm on the domain knowledge features, because we want to actually have a reason for using malconv. We don't want to use it just to say that we're doing deep learning. And so training the passive-aggressive algorithm on the original features at first glance seems to have comparable accuracy in AUC, but when you adjust the decision threshold to get a false positive rate of 0.1%, the true positive rate drops to 2%. And the kernelized version of passive-aggressive really doesn't do much better. So these three options sort of are immediately off the table. So at the hard false positive results, so that was on the training test set. Now we're looking at the results on the hard false positives. So gradient boosted decision tree gets all of them wrong. That's the fixed column here. Passive aggressive approach gets 60% of them wrong. With SGD, it actually seemed to learn a decent solution. It started off with only 38% of them wrong. But what we're going to test is an adaptive scenario. So 200 random trials of a false positive comes in. We update the model if it's making an error. And then the next one comes in and see, is it still making an error on the next false positive? If not, if so, we need to fix it. If not, good, we're doing a good job at reducing future false positives. And in this adaptive scenario, the passive aggressive approach gets our error rate on these hard false positives down to 4%, whereas SGD barely changes down to 26, and the gradient boosted decision tree can't be updated at all. And looking here, we can see that the passive aggressive approach works sometimes often with as few as one update. Only one false positive had to be fixed. We can also see the impact on global performance as we do these false positive updates. And we can see that AUC is actually pretty stable, and the estimated impact to AUC is near 0, which is good. The true positive rate does decrease over time as we do more updates, which is understandable. And the fact that the true positive rate decreases but AUC remains stable means that we can actually fix this by just sending the model back to Elastic and recalibrating the threshold for decisions. And then we get exactly the same performance as before, but no hard false positives. So though true positive rate does decrease by up to 50%, the false positive rate drops by 23 times. So it's actually still a reasonable trade-off, especially when you have an issue that is false positives. And we can also see that by testing our AUC impact estimate on the test data, by randomly swapping the labels to force errors to occur, that we do actually do a good job of estimating the AUC impact. And we see a linear relationship between our estimated impact and the true impact. So we can actually use this to help correct for errors. And now I'll take it back to Bobby.
An environment. We hope that we present an alternative kind of option to help start to mitigate some of these FPs locally without relying on current, more antiquated techniques. And we also believe that approaches similar to this, passive aggressive, will encourage kind of a safe customization and also allow us to start to establish transparency between the vendor and the user of this software to give them an ability to reduce false positives locally over time while safeguarding them from doing anything catastrophic. And yeah, that was it. Thanks everybody for watching, and yeah, take care.